Hello, good afternoon. How is everyone doing today?
Doing good. How about yourself?
Good, thank you. All right, so today we're going to be working on lab 8. So we're more than halfway through all our labs. This is about rotational dynamics. It's like the Newton's second law, but Newton's second law for rotation. Because here our lab is quite much ahead of our lecture, and I'm pretty sure no class have talked about the rotational dynamics yet, so that we will have to spend some time to talk about the concepts before we can talk about what we're trying to measure. Okay, so we'll spend some time to look at the concepts first. First, let's introduce the idea of something called a rotational inertia. We know that the word inertia was historically used to describe when the object is moving, and unless there's a force acting on it, right, it will maintain that status of motion, which for nowadays we know it's Newton's first law. So mass is a way to describe that kind of a feature of an object, because in order to change the motion of an object, you have to give it a force. So let's think of this in analogy to Newton's second law. So what does Newton's second law say? It says the F net, all the force acting on an object, is the mass of the object times the acceleration of that object, right? So this is Newton's second law. So mass describes how hard it is to give an object a certain acceleration. The bigger the mass, the bigger of a force it requires to give such an acceleration. And rotational inertia is the sort of the equivalent of mass for rotation. Okay, just like how an object with a large mass make it harder to accelerate, an object with a large rotational inertia will be hard to rotate. So think about that in the analogy to mass and translational motion, right? Acceleration is translational. Now we're talking about rotation. So the definition for rotational inertia is, well, it's actually simple enough to understand. It depends on both the mass and the radius that you're rotating with. Think about that if you have a little mass and you have a string and you're rotating around in this direction. What would make it really hard to rotate? The mass bigger or smaller? It makes sense to say, well, the more mass it is, the harder it is to rotate, right? What else would make it hard to rotate? When the string's longer or shorter? What do you think? Longer, yes. The longer the strain, the harder it is to rotate. So for rotation, both the mass and the radius will make it harder to rotate, and mass times radius squared is this quantity that describes the rotational inertia. So this is as the equivalent for what mass is in Newton's second law. Okay, so rotational inertia for a point object, an object that we can consider it as a point, is simply mr squared. If you have multiple objects, a bunch of points, you can add them all together, right? If you have a continuous distribution, one little mass becomes dm instead of a summation, you have a integration. Okay, so that is the first concept we want to talk about rotational inertia. The rotational inertia, this you will see later in the lecture. For different shapes, we'll have different formula. For a ring, you can see that, well, right now, I showed you a little point particle. But imagine if I have around this ring, I add another m, right? And another r. I have, so 1, 2, so it's mr squared plus mr squared, 2mr squared. If I add a third m, I will have a third mr squared. If I have a fourth m, I have a fourth mr squared. So for a ring, it looks, you can view it as you have many little particles but all of them are at the same distance away from the center. And all of them, every little of them is a little mass, and they are all added together, so they become the total mass m. So for a ring, simply the rotational inertia for a ring is the mass of the ring times radius squared. But for today's lab, what we are dealing with is not a shape of a ring. It is a disk. The shape of the disk is a little bit different. Some of them are very, very long and thin, and then you have a very short and fat disk. But no matter what it is, it's always a cylinder or a disk. And for a cylinder, the formula for rotation inertia is 1/2 the total mass times r squared. In fact, it makes sense why this is not like a ring, because not all of the mass are at a radius r away. Some of its mass is at a much smaller distance away. So overall, make it easier to rotate than if all the mass has concentrated on the outside, but now some of the mass is towards the inside. So that's why this is a little bit smaller. And don't worry too much about derivation of all these formulas. Usually for rotational inertia, the formula will be provided, or you can always look it up, okay? But we had already talked about why the 1/2 makes sense. So it's good to understand that qualitatively. So we will do this lab. We will look at the rotational inertia of an object mixed with 3 different parts of a cylinder, a very long cylinder on the 2 sides, and a very short and flat cylinder in the middle. Okay, so we're going to try. The goal of this lab to find rotational inertia for this wheel, for this shape. And we're going to find it 2 different ways. One way is actually the part B, but I want to talk about part B first, because part A involves taking in experimental data, and we will save that a bit later. First, you can find rotational inertia theoretically. Simply, well, didn't you tell me that the rotational inertia for a disk is 1/2 mr squared? That's theory. I could use that theoretical formula and simply plug in the different masses and different radius. I can tell you what the rotational inertia for the 3-part cylinder added together, simply using the equation. So this is based on the theory for a disk. Okay, so that is our theoretical basis. And then we can find that experimentally. But first, let's talk about how do you find it theoretically. Theoretically, you have 3 different wheels, which means the rotational inertia for this entire object is object 1 plus object 2 plus object 3. Because this is really just a scalar, like if you wanted to add up the masses, right? You would say mass 1 plus mass 2 plus mass 3. Each of the parts is a disk. Simply, they are shaped a little bit differently. So if I want to find the I1, I will use mass 1 times R1 squared. And mass 2 is M2 and R2 squared. Mass 3, I3 is mass 3 times R3 squared. That's purely using my theory. We cannot, in our lab, we cannot take it apart and chop it apart and measure each of the mass separately. All we know is the total mass. So we need to do a little bit substitution for the individual masses, because we don't really know what it is, right? So what is mass 1? Mass 1 would be the density of this entire wheel. They're all made of the same kind of material. They all have the same density. So its mass is density times what quantity? So mass of wheel 1, cylinder 1, which is
volume times volume.
Times volume 1, very good, volume 1. So here V, this V is volume. Okay, so capital V. So don't think about velocity. This V means volume. The density times volume 1. Volume 1 we can calculate because we know the dimensions. We can measure the dimensions. We know that volume is simply pi r squared times L. So V1 is pi R1 squared times L1. V2 is pi R2 squared times L2. V3 is pi R3 squared L3. So all of these you can measure and you can calculate. Now, the only thing we don't know is density. But density of the first section is the same density as the second section and the same density as the third, because they're all made of the same kind of metal. So if I can use the overall mass divided by the overall volume, V total, then I can get my density. So overall mass is whatever the wheel, it tells you on the wheel what the mass is. And the overall volume is all of these three parts added together. And each of the parts we know how to calculate, right? So eventually you have changed this formula, you have derived such a formula for the theoretical value for your rotational inertia for the wheel. The three parts wheel is 1/2 total mass, and volume 1 R1 squared plus volume 2 R2 squared plus volume 3 R3 squared divided by the total volume of all of them added together. So that's simply derived from this derivation. Okay, so if you plug in M1, you get, and you plug in M2, just like how we did, you will get this formula. Okay, so this is pretty much all the same as how you would do the pre-lab. So pre-lab, instead of a 3-wheel, you have a 4-wheel, but the math is very much the same. All of the 4 different wheels are in the shape of a disc or a cylinder. So each of them follows a 1/2 mr squared formula. So to calculate the rotational inertia for each one of them, right? So they all follow the same formula. You just have to calculate the volume separately. So let me write out everything. I4 is 1/2 m4 R4 squared. Okay, so you can see what is given is the radius 1, 2, 3, 4, the length 1, 2, 3, 4, the total mass, but it didn't really give us the individual mass of these different wheels. So we need to do a substitution that the mass 1 will be the total mass divided by the total volume times volume of V1, okay, and times the R1 squared. So we substitute M1 by this formula, okay? Density times volume is mass 1, okay? And then the same thing for the I2 is overall mass divided by the total volume times volume 2, R2 squared, sorry, this is R2 squared. So we made a substitution of M2, and the same thing for 3 and 4, okay? You can see the volume for each of them is pi R1 squared L1, okay, pi R2 squared L2, or R3 or R4, okay? So the formula is the same for all of them. So you can plug in your volume for each of them. You can plug in, and you know the mass, you know the total volume, and you know the different individual radius. So you can do the calculation. I have a solution here that I simply plugged in the variables and sort of simplified my answer as much as possible, and I reduced everything to the final expression where only the known quantities are left. So everything is expressed using radius and length. I canceled out everything else, substitute everything else. But you could calculate the V and then get a number and then plug it in. So you can plug in numbers at this stage if you want, okay? Or you can do it like me, do a little bit more substitution and plug in numbers later. So it's not different. You will eventually get the same answer. Okay, so I want to ask, Are there any questions about, so let's go to our lab. Are there any questions about how to calculate the rotational inertia theoretically? And then if there's no questions on that, we can move on to how to measure the rotational inertia time using experiments.
So the formula for the theoretical formula there,
Mhm.
that one is the same as using just half times mass times radius squared. Because
This is the same as this?
yes.
Yes, they are the same. The problem is, well, this is simply from the definition. Okay, what is our definition for rotational inertia? But we don't know what the individual mass is. We cannot take it apart to measure it. So instead, we do know what the overall mass is. So we did a little substitution, and then eventually the equation you will use is this equation that I put in the box, that everything is expressed using the total mass and the individual volumes, which can be calculated from the radius and the length. Okay, so this is the equation you are going to use. It comes from here.
Okay.
Okay. There is a question in the chat that asks, what is the denominator for density? For density, the denominator is the total volume. So the density of any parts of this material is, so this material is made, these three parts are made of the same material. So the density of this material is the total mass divided by the total volume of the entire object, right? And the volume is V1, V2, V3, three different volumes combined, and the total mass is already given to us. So all you need to measure in the lab is radius 1, R1, radius 2, R2, radius 3, R3. And you can plug into this formula to calculate it. Did I answer your question? Was that clear? Okay, so so we pretty much figured out how to do this theoretically. We'll take a really quick look at the video on the last part. We will come back to do the part A later, but now we just want to get the theory part out of the way, okay? So this is part A, but I'm going to actually jump to part B, show you where they are measuring the different radius. So part B. Okay, so that is length 2. That is the length in the middle, okay? 15.61 millimeters. That is length 2. Okay, so you want to keep all your units consistent. So if you use all SI units, convert that to meters before you plug into the equation, okay? Now this would be L3, okay? This is measured L3. So 51.71 millimeters, that is L3. And that is L1, the length of the first centimeter. Now they're going to measure the diameter. They cannot get radius, so they get the diameter. So you divide it by 2, and that's your R3.
With these dimensions.
So the one that they're just showing you, the 30.26, that is the diameter of wheel 3. Okay, divide that by 2, you get R3. Now, the tricky part is now they're going to measure, trying to measure at least R2. But notice that they cannot get to the center of the second wheel, okay? They can only get to as far as the third wheel, the rim of the third wheel. So
that concludes the rotational.
So they measured 85.4. Okay, that wasn't very clear. What is the number?
Dynamics.
85.4. So how do you get the radius of the second wheel? The one that you measured, I will tell you it's not exactly the radius. How do you get?
Concludes the rotational.
So from 85.4, what do you have to do in order to write down R2? Anybody would like to share their thoughts? So R3 is 30.26 by 2 divided by 2. That's correct, because that's the diameter you measure divided by 2. But the 85.4, you know, it's not the diameter. It is close to the radius, but it's not as much close to the center. What do you need to do in order to get to the center? You can see yeah, you need to add it, the radius of R3. Very good, Giovanni. You do need to add the radius of R3, which was about 15 millimeters that you measure from the previous step. You need to add that onto 85. That is your R2, okay? So they will show you, and then lastly, they will show you R1, and then after that, you're pretty much done with all the measurement for trying to calculate
Can you repeat that last part? I dropped out.
Oh, the last part where I talked about what R2 is?
I think you were talking about calculating the radius or something like that.
Oh, the last part was in the diagram, what they, in the video, they measured from here to here, okay? They measured this to be 85.4 millimeters. So I was saying that is not quite the radius for R2 because they not poke it to the center. So to get R2, you need to add that, the radius of R3. You see, you need to add this little part to get the entire radius of the second cylinder. So you need to do 85.4 plus 36. I don't remember what that is, 0.02, something like that, divided by 2. So that is the radius of the third cylinder, which is this little section, and add what you measured. All of that together will be the radius of the second cylinder. Did that answer your question? Okay, so
Yes.
that is one little very subtle part. Be careful with the data. Okay, so now we how to do the rotational inertia theoretically. We also need to find it experimentally. Okay, so this is the one last slide where we have a lot of information, but we will do it slowly. So Newton's second law, I'm sure you're all very familiar with Newton's second law, because to apply Newton's second law on an object, you simply say F equals ma, right? So what we're doing in this lab is you try to make the wheel rotate by using a weight hanging down the string. So this is a weight and this is the string. You can see as the weight goes down, the string unravels and the wheel starts to rotate. If we apply Newton's second law on this mass, on the weights you added, there are two forces, gravity and tension from the string, just those two forces. So we can apply Newton's second law on it. Gravity minus tension is the net force that's equal to the mass of the weight times the acceleration of the weight. So you can have an equation for your tension. The acceleration, you can see this is a linear acceleration. This tells you at what rate your your string unravels, which is the same acceleration as at what rate that your object is going down, is speeding up downward. But it is related to rotation because as your string unravels one circumference of the smaller wheel, your entire object had rotated one revolution. So a linear acceleration is related to an angular acceleration simply by multiply that angular acceleration by radius r. This you have already seen something very similar in the previous lab, is linear velocity is angular velocity times radius r. Okay, so linear acceleration is angular acceleration times radius r. So that's very similar. So you might wonder, okay, why do you want the angular acceleration? because we want to write Newton's second law equivalent in rotation. So Newton's second law tells us, okay, what causes an acceleration? It is the force. And we can ask the same question is what caused a rotation? So originally everything is at rest. A force gives it an acceleration, starts moving. And what gives it an angular acceleration so that it starts rotating? So and again, using that analogy idea, for it to rotate, mass becomes rotational inertia. Acceleration becomes angular acceleration alpha. So force becomes a quantity you probably have already heard is called the torque. So just like how force makes something accelerate, torque makes something rotate. When it was originally at rest, it starts to rotate. So torque is equal to I alpha is Newton's second law for rotation, okay? We also call it Newton's second law for rotation, or someone might call it, this is what we know for rotational dynamics. So torque is equal to I alpha. The alpha is how fast the wheel are spinning up as it rotates. So it's the angular acceleration, I alpha. And the torque can be calculated by using the tension times how far the tension is, the string is away from the center of the axis of rotation. So there is quite a bit of information here. Well, basically, we all have a very good intuition about torque. Okay, torque is like when you try to use a wrench to loosen a bolt. Of course, the more force you apply, the more of a torque you can generate. But it also depends on where you're holding that wrench. Do you want to hold it closer to the bolt or a little bit further down so you have a longer level arm? You probably want to give yourself a longer level arm so that you can generate a bigger torque, right? Just like when you open the door, where do you usually try to open it? From the edge of the door or right at the hinge? If you try to really push hard at the hinge, do you think the door will open?
No.
It wouldn't, right? Because you're having a very small level arm. That R is small and the torque is small. So for you to have a big torque, you want a bigger force as well as a bigger level arm. So here the force is our tension, because tension is the one that make it rotate. The level arm, let me try to draw it on the diagram here. The level arm is from where the force is being applied. The force is being applied right here. And it's rotating relative to this center axis. So from here to here is your level arm, which is simply the radius of my third wheel, R, okay? So tension, you already got it from the previous step, plugged it in, multiply the R, and you can see that you can find what this torque is. So in our lab, what do we measure? We have our photo gauge set up. So there are little spikes coming out of the wheel, these different, we call it triggers. So as it rotates past the sensor records the data. So we are measuring the angular acceleration. So alpha is what you measure. But from alpha, you can plug it into this equation and you can get torque, okay? And if you plot a y versus x using all the torque data and all the alpha data, you should get a linear relationship, because we said Newton's second law for rotation says torque is proportional to alpha, is I alpha. So the slope of the graph that you get will be your rotational inertia measured using your experiment. You can compare that with what we just got theoretically. There is a little bit friction in the system, of course, so you will have a y-intercept and then tell you how much torque is generated due to friction. Okay, so there is another y-intercept. So in our data, we will read all the different alphas from the lab. So it doesn't matter which stages you're in, right? You just record the alphas here, and you record the corresponding mass that you added, and you generate the torque, and you plot, eventually you plot alpha versus torque, and you get your graph. Okay, so let me go back to this slide before we look at the video. Are there any questions? Yes, go ahead.
Yeah, what's that, the formula at the top? V equals that angular speed or times
Angular
radius?
velocity times r, radius.
Well, so what's V in that equation? Volume?
Oh, v. This is a linear velocity or linear speed, and this is angular speed. So I'm showing how do you relate a linear quantity to an angular quantity is simply by multiplying by the radius. That's just like how we relate the linear acceleration to an angular acceleration. We multiply it by the radius.
Okay, thank you.
Thank you. Any other questions about this particular slide?
Yes, I have a question.
Yeah.
Well, you kind of showed it in the other slide, but how are we gonna find the angular acceleration? Or we would have to graph first, and then from
Angular
there.
acceleration, you will read it directly from the video.
Oh, okay, okay.
Yeah. Mhm.
Okay.
Take my car to pick up Ariel.
Any other questions?
Sorry about that.
No problem. Any other questions? So if there's no more questions, we're going to look at our video, okay? So,
Oh, you know, I did have another question, but
Uh-huh.
it is regarding the pre-lab.
okay, go ahead.
The question I had was, I guess I tried doing both methods. Like I tried doing the method that you were talking about with calculating the mass for each cylinder.
Mhm.
By using the I didn't know that was the full density of if you get the total density, then that's the density for each item as well. I did like that, didn't click in my head.
Yeah, that's true.
But when I did, do that part,
Mhm.
I got a different answer. Does that mean that doing it that way is less accurate than the formula that you're giving us now?
You shouldn't get a different answer. I mean, you can calculate individual masses. You can, okay, first of all, you can calculate the density for the entire object, right? By using the overall mass divided by the total volume added together. You can get you can get this density, and you multiply the density by different volumes to get the different masses. So it shouldn't give you, you mean you give a different answer for your rotational inertia as a final result?
Well, I mean, it wasn't way off. Like when I used the formula that you gave us, I got 2.2 kilograms per meter squared. And then when I did it with just the density, I got 2.10 kilograms per meter squared.
Oh, okay. In that case, it simply could be a rounding issue.
Okay.
Yeah, so I wouldn't consider those two that drastically different, because it could be that when you were doing density that you had rounded and then plugged it in, so subsequently changed by slightly a little bit. So
yes,
these
that's
are
true.
they're not considered different. They're still the same.
Okay. All right. Thank
So
you.
it's simply just a rounding problem. So there's no worries there. Thank you for pointing that out. Let's go to take a look at the video. Okay, so I want to tell you that with our data, we are wrapping around our strain on the smaller wheel. So A10, step A10 in the lab manual is for wrapping around the string on the big wheel, and we're not going to do that. Also, it will show you that data in the video, and you simply just jump through. We're not going to look at that particular part. So let's look at A1 to A9. So part A, is it 150 grams they started? Yeah, 150 grams. So they start out the lab with 150 grams and added, you want to write 0.15 kilograms because our data is using SI units. I believe what the previous one, 0.150 grams, they give you a slope. If you can see the slope, that's your acceleration, angular acceleration. You want to write down 0.71. That's your first alpha. The second mass they use is 550 grams. You will write 0.55 kilograms. They'll show you the second slope. Okay, so the second slope is 4.26. That's your alpha for the second data point. And they will do this for 3 more different masses. And then they will do one for fun. And let's see if we can jump to that part. So this part for fun is 650 grams, and then they will get a different slope as well. Okay, 5.12 is your acceleration for the 650 grams. And then eventually they will do one with no mass added. So there's 0 force. Okay, here, but before we get to that, they will do part A10. You're not gonna do any data recording there. That's wrapping the string around the large wheel. We're actually gonna skip that. And you can jump through where they do part A11. So, okay, this is part A11. Torque is 0. So if there's no torque, it's not going to have any acceleration, right? So you simply give it a spin. It will. So if there's no other forces involved, it should just spin with that constant velocity because there is no acceleration. You haven't added any weight to make it spin faster or slower, right? So they will record their data. You would pretty much expect to get a constant velocity, but yet it is not quite constant. You can see it actually slowed down a little bit. Is this velocity data expected? Well, there's nothing to give it an acceleration, so you have to manually rotate it to let it start rotating. And you can see the velocity is pretty constant, right? So it is expected because it should maintain relatively the same uniform speed, but there is a little bit of a slowing down, and that is due to friction. That's how we get some information about friction. And reflected on your data, you can see it slowly kind of slowed down a little bit. And this particular slope, negative 0.45, is the alpha you will record for the 0 mass added. The last row, your alpha is negative 0.45. So that concludes all of your data collection. And after you're done, you will plot alpha and you will plot the torque, and the slope that you get should be your rotational inertia. And you will compare that to the ones that you calculated using the formulas you calculated theoretically. Okay. Any question about the data collection so far? Any questions about what to record and how to calculate?
Yeah, I have
Yeah.
one question.
Yeah, go ahead.
For the torque, since we are converting it to kilograms, do we use 9.8 for gravity?
Yes, you will use 9.8. You will use all the kilograms for your masses, and your alpha, whatever data you raise here, you will use that is in the unit of radians per second square, and simply use G 9.8 meters per second, and that's torque. It's already in the SI unit.
Okay, thank you, Dr. Mary.
Very good.
I have a question.
Yeah, go ahead.
So I'm looking at the worksheet as well, and I want to know, how would we find R?
R, you're wrapping it around the smaller wheel, so your R will be your radius for the third wheel.
Okay, okay.
Right, that was the 30 point something divided by 2. That was the data we looked at earlier.
Oh, right,
Yeah.
right, okay. So we would do that for, okay, but like, the worksheet has like the smallest wheel.
Yeah,
then it
that is
has-
the smallest wheel.
Right, and then it has largest, but then it has another alpha between, another alpha between, another alpha between. What would we do for
Oh.
that?
Yes, so that one, the first two, so okay, this is the order I listed in the order of the first mass they used actually give you the smallest alpha. The second mass they use give a largest alpha. So simply just record it according to the order that they showed it in the video.
Oh, okay, so as it's going, then record it. Okay,
Mhm.
okay.
Yeah.
All right, thank you.
Right, there is more data in the video at A10. When they start showing A parenthesis 10, you can ignore that they start wrapping around the larger wheel, and we're not going to do that. We're just going to use a small wheel. Okay, so that concludes the data collection, but there is a very subtle thing I want to point out in case if you discover it on your own, is so how do you think our sensors are able to get the angular acceleration? So, okay, we know that you measure velocity and the slope of the velocity is acceleration. So we read the slope, that all makes very much sense. But we want our acceleration to be measured in the unit of radians per second square. So which means our velocity should be measured in the units of radians per second, right? So in order to do that, you have to tell, now if you were to do this in person, you have to tell the computer when you enter these, okay, thickness of the blocking, that's when your spike passing through the sensor, how many blockings, so when it pass through the sensor, the 7th passing through, that's rotating 2 different revolutions. You have to tell the computer for 7 blockings, that is 2 rounds. So if you want to get a angular velocity and eventually give you an angular acceleration, you need to tell the data that is 4 pi, because 4 pi is radians. So you have to enter 4 times 3.14, that is 4 pi. And then the units the computer gave you, because computer doesn't care about units, it tells you whatever you want it to, right? So you will tell the computer is 4 pi. And then the data will be in radians per second, and acceleration will be in radians per second square. But there was a little mistake in the video. I mean, and they didn't show it here, but if you look at the resources on the physics website, the video there, they actually added description saying there was a mistake in the video about they were actually using the circumference of the small wheel. So they were doing that because they wanted to give you a linear acceleration. Okay, so once you get a linear acceleration, you still have to divide it by r to get the angular acceleration. But that's totally unnecessary, because you can simply tell the computer to use radians to begin, and the data is already in alpha. You don't have to do any conversion. But how come we can still use this data is because it just so happens the mistake they made coincides with what we wanted for a radius anyway. So they actually made a mistake in the circumference so that the new number 14 they entered is pretty much close to 4 pi. And so the data actually worked out. If you treat the data as alpha, the I you calculate will be pretty close to the actual I of the experiment. So there's a subtlety I do want to point it out. If that confuses you, just forget everything I said. You can just take data as how we were talking about. But if you wanted to look a little bit further, I had just explained it to you that there is indeed a little mistake in the data, but just by coincidence, they mistaked, the number of the mistake worked out, so we can still use that information. Okay. Any questions about this lab? Any questions? All good? Okay, no more questions. All right. All right, so if you do run into any more questions, feel free to email me. And if not, I wish you the rest of a good rest of the week and see you guys next time.
Professor?
Yeah.
I have a question. I just took a look at the video and I noticed in the description of the video that's on Canvas, it has the link to another video that.
Right, that is what I talked about. They're saying there is a little arrow in the description, but we actually can ignore it. The mistake they made happened to work out, that if we treat it as a radius, the alpha that measure, the slope that measure is simply is the alpha we need. Okay.
So if we use that second video, will we get the same? Our lab will still be correct.
Okay, if you use a second video, then the slope they give you is a linear acceleration. It will not be an angular acceleration. And you have to divide all the data you take from the second video by the radius r of the third smallest wheel to get the alpha. But if you use the data in this video, you can take the slope directly as the alpha.
So you recommend we just use the first video?
I recommend just read video and treat it as a radians and give us correct data for alpha.
Okay, thank you.
Mm-hmm. Any other questions?
Well, I have a question, but it's not. It's regarding the same thing, but just a question. Like, so if we had the same kind of data, but it was like in degrees instead of radians, for like say for some other problem.
Mm-hmm.
What do we do to convert it? I know you can just use a calculator, but what's a way to do it mathematically, convert
Sure.
the degrees to radians?
Oh yes, sure. So if you go all the way around, that is 360 degrees, and that is equal to 2 pi. So you can use that conversion to help you. So 360 is 2 pi. So if this is 100 degrees, and that is how many radians. So you can set up that proportion to calculate it. Does that make sense? Yeah. So you can do that to convert.
Okay. Thank you.
Any other questions? Okay. All right. So I will see you all next week, and have a good rest of the day. Bye, everyone.
I guess I got a little confused regarding that because I remember like an old teacher, she told me to divide by 57.3, and I was just.
Oh, well, that's just 360 divided by 2 pi. That proportion give you that number.
Oh, okay.
Right.
That's that fraction in as a real number. Okay.
Yeah. Or maybe the other way around, but I don't recommend you try to memorize a specific number. It's much better to understand where it's coming from, and you can always refer to your understanding, right? So always set up your proportion 360 divided by 2 pi is equal to, okay, whatever degrees you have now, let's say 100 degrees divided by how many radians. So the radians would be 100 degrees over 360 times 2 pi is your new radians.
All right, thank you.
All right, bye-bye, everyone.